Hello everyone, my name is Dylan Rood from Imperial College London in the UK. Today I'm going to be talking to you about cosmogenic radionuclides, principles, and laboratory techniques as part of Geochron January. First, I want to thank the IGCP 725 team for inviting me to give this talk. Before I begin, I'd like to acknowledge the significant contributions from the wonderful and talented team that I've worked with over the years. Colleagues Martin Hurst at University of Glasgow, Klaus Wilken at ANSTO, PhD students Jennifer Shadrick and Susanna Surad, master's students Beth Hebditch, Alex Seal, Emily Gusterson, and Jay Ward. First, some key takeaways from this talk. First and foremost, rock coast cosmogenic radionuclide applications are hard. Pardon the pun, but they really are. The concentrations in these samples are 2 orders of magnitude lower than pretty much anything that is routinely measured with cosmogenic isotopes. And so it is a very challenging but rewarding endeavor. There's a lot of essential requirements that I'm going to be walking you through in order to successfully apply cosmogenic radionuclides to rock coasts. But ultimately, it's worth it and feasible now because they provide unique and important data on past and future coastal change and processes. I'll begin by discussing some of the principles behind cosmogenic radionuclides. First, their production. Cosmic rays are constantly bombarding Earth from outer space. Those cosmic rays enter Earth's atmosphere and produce secondary particles, including fast neutrons and muons, which have high enough energy to disrupt the nuclei of elements contained within crystal lattices of minerals. So in this case, we have a cross-sectional representation of the Earth's surface here. Quartz grain sitting near Earth's surface, that has an oxygen-16 atom in its crystal lattice. One of those high-energy fast neutrons interacts with the nucleus, causes what's called a spallation reaction, where the nucleus is actually blown apart, and what is produced is a beryllium-10 atom, which is the cosmogenic nuclide, and some subatomic particles. And so these spallation reactions occur primarily derived from neutron interactions in the first few meters of Earth's surface. So their production rate and therefore their concentration will be at a maximum at the Earth's surface and then decrease exponentially according to the attenuation length of that nuclear reaction over the first few meters of Earth's surface. What's important to understand is there's a suite of cosmogenic nuclides that include both radioactive and stable isotopes that are produced by these cosmogenic production pathways on elements that are common in rock-forming minerals. So I'll be mostly discussing beryllium-10 and aluminum-26 today, which are the most common nuclides that we've been using. The 2 things to take away from this are first, that cosmogenic isotopes are uniquely produced by this kind of nuclear reaction at or near Earth's surface, and also that we know the cosmogenic isotope production rate, and it's dictated by the nuclear physics, which is also very well known. And if you're interested in the details of this, you can do some further reading from these 2 kind of classics. So in the context of rock coast cosmogenic radionuclide applications, that cosmogenic radionuclide concentration, this quantity N, which is in units of atoms per gram, at any depth, as it evolves through time, can be expressed with this equation, where we integrate the left-hand side of the equation, which is the production of the cosmogenic radionuclide, and then we subtract the right-hand term, which is the radioactive decay. And so here the production rate it basically decreases exponentially as a function of depth and also the attenuation length of the nuclear interactions, whether that be neutrons or muons. And that production rate is scaled as a function of the topographic shielding, the geomagnetic shielding, and the water shielding in the case of these rock coasts. And so if we collect a suite of samples across the rock platform, as you can see here, in cross-section at increasing distances away from the cliff, we can reconstruct the history of that erosion from those concentrations. And so conceptually, this is kind of showing how that works. Basically, what we would expect to see in kind of a plot of increasing distance away from the cliff as a function of cosmogenic isotope concentration, in this case beryllium-10 concentration, we end up with this kind of typical humped profile, whereby as rocks are exposed for more time, they have a higher concentration, but as you go further out offshore, you also have increased shielding from the water, and so that actually decreases the production rate, and so you then end up with this humped profile. And basically the amplitude of that hump will be proportional, or inversely proportional, excuse me, to the retreat rate, with a higher amplitude hump being slow retreat and a lower amplitude hump being a fast retreat rate. There's one other thing that's important here, which is this idea of inheritance, that basically prior to this platform being formed, there was some production by deeply penetrating muons within the cliff. And so we basically can correct and subtract out that inherited component, that component that basically was produced prior to the formation of the platform, using the lower equation here, which basically solves as a function of depth for the nuclide abundance, the concentration of the muon produced beryllium-10, assuming a steady state surface lowering rate, this erosion rate in millimeters per year. And so effectively this becomes this kind of background rate, and we characterize that by collecting a sample either from the sea cliff or, in an ideal case, from a sea cave, something that's completely shielded at a depth that is similar to the depth of the platform samples. And so, of course, what this means is that the first step in conducting this research is going out and collecting the samples to measure those cosmogenic isotope concentrations in. These are just briefly two examples, one from France and one from England, where these studies were conducted. And again, they just share that similar quality of collecting these transects across the shore platform from near the cliff, modern cliff, at increasing distances out offshore. And then, of course, Susanna's study in Yorkshire also incorporated the correction for that inherited muonogenic component, which was, in this case, was very significant because of the low concentrations measured in these samples. The other thing that's important to collect in the field, of course, is the locations. You need detailed locations of each of these samples. That's usually done with differential GPS surveying. The other thing you need is the topographic profiles of the platform itself, which is usually either collected through, again, differential GPS surveying or through a combination of LiDAR and bathymetric data. Or in our cases as well, we've used drone photogrammetry on the platform to collect that topographic information as well. Another essential component to applying cosmogenic radionuclides for rock coasts is the implementation of a numerical model. I'm not going to go into the details of this here because I could give a whole other talk just on it, but the basics are that there are kind of two different types of numerical models. One are these, what was initially used were these geometric kind of equilibrium retreat models, where the topography just kind of observed today translates through time. However, what we've done now in the most kind of up-to-date version of these numerical models is to couple a process-based coastal evolution model of Matsumoto et al. To a model of cosmogenic radionuclide production called RoboCop that Martin Hurst developed. And that coupled model basically has three inputs: that topographic profile that I mentioned, a beryllium-10 profile that I talked about, and then a relative sea level history. And that basically, those three inputs go into that coupled model and simultaneously optimize for both, basically using two objectives: one using the topographic profile, root mean squared error, and the other for the beryllium-10 profile. So they basically optimize both through the concentrations and the topography. And we've been using this Dakota software package to do this optimization, and without going into the gory details, we get a maximum likelihood estimation out of this. And so what you can see here on the right is the outputs of this RPM model for two sites in the UK. And this is basically showing the optimization, the most likely estimate results for both Biddeford and for Scalby, using a different variety of weightings of topographic versus beryllium-10 in the optimization to form this kind of Pareto front. I'll leave that at that, but I'm happy to talk talk about this more in the breakout session. So in terms of moving on to laboratory techniques. So first I thought I would just start by saying, why these laboratory techniques have evolved the way that they have. And basically that's because back in 2012, Vincent Regard and his colleagues published this really fantastic paper that was the first of its type to really dig into, as a proof of concept, of using these beryllium-10 concentrations to model cliff retreat. And it really caught my attention and the attention of myself, Martin Hurst, and Mike Ellis at BGS. And we got together with Bob Anderson and really started scratching our heads about this. And the bottom line is that I got very excited to get involved because this is a perfect example of the use of a numerical model with the cosmogenic isotope concentrations. And in their case, they were really limited by the precision of these incredibly low concentration samples. So these are beryllium-10 concentrations in thousands of atoms per gram. That's 2 orders of magnitude lower than most samples that you would conventionally measure. And so whereas the uncertainties on these analyses were very large in 2012, this is what they look like today. We've done a lot with the chemistry and analytical methods to reduce those uncertainties. And we're now to the stage where we can get really, really nicely optimized results and also actually even measure 2 isotopes, both beryllium and aluminum. And you can see the error bars on these compared to these are much, much smaller. And therefore, we have much more confidence about the cliff retreat rates and also the age of the cliff, or the age of the platform development from these data. So then with that in mind and kind of the motivation for why we are doing this and working so hard to get these laboratory techniques optimized, this is kind of a very busy representation of the laboratory workflow, but there's basically just these kind of main steps. There's the mineral separation, which is basically kind of in this part of the diagram, mineral purification, which is in this part of the diagram, which is mostly, in the case of quartz, acid leaching and etching. We then do isotope dilution chemistry, whereby we take a certain amount of mass of quartz, we dissolve it in the presence of a certain amount of a carrier that we add, and effectively then we purify out either the beryllium or the aluminum from that solution through a succession of chemistry methods to purify out those elements. We then take that material, that element, and prepare it for accelerator mass spectrometry, and then analyze it with accelerator mass spectrometry. The key thing here is the quality assurance, that at every step along the way, we're monitoring the cleanliness and the purity and making sure that everything that we added when it comes out at the end is very pure and quantitatively covered, because that ensures the highest precision and quality of the analyses to achieve those small error bars. And so to kind of just show you a little more pretty pictures of what the lab work actually looks like, this is again showing that quartz purification step. We're basically working with hydrofluoric acid, got the whole PPE set up, working in fume hoods, plastic fume hoods. They're capable of working with hydrofluoric and perchloric acids. We're again using an ICP optical emission spectrometer to do all sorts of testing, both of the quartz and of the fractions all through the chemistry to track and trace everything that we do to make sure it's, of course, of the highest purity and that we're getting all of the beryllium and aluminum out of the sample that we put in. This is ion exchange chromatography that we use for these coastal samples. You can, if you've seen these in other labs, these probably look like they're on steroids. They look really big because they are really big. We use large columns because we have large cation loads that we have to deal with, and I'll explain that in a second. But again, these are kind of essential for these large samples and potentially dirty, meaning high cation load samples that you have to use for these coastal applications because of the nuclei concentrations are so low. And then we have specified places where we do the target preparation, working with beryllium, which is a hazardous material itself, but using the most clean and reproducible results as possible. So in terms of purity, this is just kind of to focus on that for a second, because it really does matter. This is some work that we published a few years back, looking at optimizing the beryllium 10 chemistry specifically. And so this plot, for example, on the left is showing a suite of cations. And on the left-hand axis, basically the load of the cations in micrograms per gram. But more importantly, on the right-hand axis, what that is equivalent to in terms of how the ion exchange columns think about it, which is the milliequivalence, which takes into account both the atomic number and also the charge of the ion in solution. And so the bottom line is here is that before we dissolve the sample, we characterize the quartz itself and make sure that it is clean or pure or whatever. But more importantly, that the whatever's in it, whatever the load on the column is going to be, doesn't exceed the capacity of the column. And so that is all very calculatable, and analytical chemists and radiochemists are very used to this, but geologists and geographers not so much. So this is really important stuff in terms of lab techniques and quality assurance. This on the right is what's called an elution curve. Maybe some of you have seen this, maybe not. But basically what this is basically a volume of solution that's been passed through the column, increasing to the right, and basically the total load and percent of the total on the y-axis. And so this is, the upper one is an example of a really clean elution curve whereby you have a very nice peak of titanium. It's very separated from the peak of beryllium, which is very isolated from the peak of aluminum. And this is for a low cation load, which is easy for the column to take and very much below the capacity. On the other hand, this is for a capacity, something exceeding the capacity of the columns, where you start to see tails overlapping, and basically that means that each of these fractions is going to be impure, and that causes significant problems in terms of target performance and precision and reproducibility, and just especially for low concentration samples, it's just a deal breaker. And so you can see that manifest in these plots. This is something we published just last year. Basically, this is showing for the final beryllium fraction, so the thing that comes off the column that's supposed to have all the beryllium and nothing else. This is showing the measured concentration, and you can see here again, this is 10 to the 5th atoms. This is 2 orders of magnitude higher concentration than anything you would measure on a coastal sample. This is the typical kind of range you'd measure normally in these applications, other places at least. And so what you can see here is this across many different laboratories and many different AMS facilities, this strong correlation between the content of magnesium and the measured concentration. This is not what you want to see, basically. You don't want there to be this correlation, and there is. And that magnesium is basically in the beryllium fraction and is causing this effect, which is not good. And also, we now trace this back to where it came from, and it came from mineral impurities in the quartz. So this is an example of where it's very clear that we don't want to be generating dirty quartz, because ultimately those things get into, or can get into, the beryllium fractions, and that will interfere with our ability to precisely measure the concentration. You can see that on the right here, because this is showing for all these different laboratories measurements of the exact same quartz, this kind of dirty quartz. And so these boxes basically are the average and 1 standard deviation of the analytical uncertainties measured for each of the samples. So these are basically, saying they're 3% uncertainties plus or minus, a few percent uncertainties. And these dots are basically the relative standard deviation. So this is basically the distance between this dot and the box. They should be on top of each other, and if there's some distance between them, there's more scatter in the data. There's more dispersion in the data than there should be. And so this is, again, showing that purity really does affect reproducibility, and we gotta control that, especially for beryllium. Aluminum, the uncertainties are just larger in general, so it looks a little bit cleaner, but the same pattern exists. And so this is just really demonstrating that that the purity will affect the reproducibility. So this is going on to the idea of yield. This is the idea that we want to get the beryllium that we put in, all of it, out. And this is for a very good case. This is what we want to be seeing, and we need to ensure in coastal samples in order to measure samples very precisely. This is basically showing the final yield from the beryllium chemistry. For the blanks, there's like a 94% yield, and for the samples, similar. And what that means is that when you get that type of quantitative yield coming from the samples, you end up with this, which is basically, this is beam current measured in the accelerator mass spectrometer, which I'll talk about in a second. And this are all basically giving high and reproducible beam currents relative to the standards measured in the samples. And this, again, is essential for coastal applications. We also need really low backgrounds for these types of work. And this is just showing plots showing the range of blanks measured in this laboratory. This is the University of Vermont in the US. And basically the idea that, we need to characterize these backgrounds for coastal applications very well. And we also need to make sure that they are well below the samples. Now, for example, this blank level is at the level of the samples that we are measuring in the coast, so we couldn't use that one. These are better, but you can see that there's some scatter through time, this is blank levels as a function of time, and there are periods of time where the blanks scatter highly, and we want to avoid that as well, because that implements additional uncertainty into our analyses of the coastal samples because they're so low concentration. So next, in terms of lab techniques, is accelerator mass spectrometry. Again, I can take a whole talk just on this alone, but you can see that this is what we rely on to measure these rare isotopes. This is a 6 million volt system at ANSTO in Australia. The concept behind accelerator mass spectrometry is that by accelerating samples, basically injecting negative ions, taking them to high energies, passing them through some material called a stripper, and then effectively accelerating a second time the positive ions, you can eliminate all isobaric interferences. So anything that's a molecule is obliterated by that nuclear interaction, and you can basically then sort the atoms by their charge and mass as elemental particles before the detector. The advantage of this is that you can measure, to cut to the chase, is that you can measure 1 in a million billion atoms. That's like 8 orders of magnitude more sensitive than any other mass spectrometer. And we're looking for coastal samples. If the blanks are 1 in a million billion, we're seeing maybe 5 out of a million billion in the samples. So we're very close to the backgrounds, and so all of these chemistry methods really matter to get the best possible analyses out of the accelerator. So what the accelerator mass spectrometer does is measure an isotopic ratio for beryllium and for aluminum, and we can translate those ratios into concentrations of the rare isotope using the chemistry information that we have from the lab. And so what this is showing is basically, as a function of that isotopic ratio for both beryllium red and aluminum blue, the uncertainty that we get from the accelerator measurements. And anything to the left of 1 times 10 to the minus 14 is kind of where we're looking, where we're measuring for coastal analyses. These are extremely low concentrations, and it is just absolutely essential that everything is done correctly in order to achieve the kind of optimal precisions that we expect to see. Anything goes wrong, and all of a sudden these uncertainties blow up enormously. So the other thing that's important is that because we're just above the background, the nature of the background and the background correction that we apply can have a huge effect on our understanding of the concentrations, that quantity n, especially at this level that's below 1 times 10 to the minus 14, where this is where we measure samples for coastal purposes. And so again, backgrounds are essential to quantify, and knowing the source of your background dictates the error. The different background corrections will kind of fall within this gray zone, and as you can see, these gray envelopes are very large and have huge background correction difference, in part huge background correction differences for these really low concentration samples. So why, you might ask, would you work so hard to do this in the lab? The answer is for this reason, for the applications, that if you can do all of these things and get them right, we've now shown that you really can get some essential information about both past and future changes in the coastal environment. This upper plot is basically showing the cliff retreat rate from our coupled model. The solid line is the cliff retreat rate for the last 7,000 years in the past, with error uncertainties in the shading, as compared to the dotted line, which is the relative sea level history. And so basically what we showed here for 2 sites in the UK was that the cliff retreat rates really tracked the relative sea level in the past. And so we then went on just this last year to publish in Nature Communications forecasts using the optimized model for the future, for the next 100 years, based on several basically sea level histories that were related to the representative concentration pathways, the emission scenarios for the future. We also, of course, get some essential information about processes acting on the coast. So for some of you who are more interested in the processes, this is an example of where the numerical model actually gets constraints on the weathering rate. So this kind of helps to address this kind of waves versus weathering controversy that has persisted in the community for quite a while. This is comparing sandstone sites over here to these chalk sites in the UK. And basically what this is showing is that only the chalk sites and the softer rock types are showing significant amounts of weathering, and that most of the sandstone erosion is being driven by wave erosion, which is of course important as well. Just to return now to my key takeaways, of course, yes, rock coast cosmogenic radionuclide applications are hard, but it is tractable and feasible, and as long as these essential requirements are met, it is totally doable. Again, we need an abundant separable mineral, whether that be quartz or other minerals, but in the case of quartz, anything greater than or less than 150 microns is really, really painful. Susanna can tell you all about that. But the point is that make sure you have abundant separable minerals, clean those minerals up, make sure they're nice and clean before you dissolve them. During the chemistry, monitor purity and yield, and to ensure that you have the purest, highest yield of the material. Assess the reproducibility as you go, both with field replicates and also of standard quartz or mineral standard materials, just to make sure your measurements are reproducible. Work on getting low backgrounds and quantifying that background very well as possible. Lots of blanks, basically. And then when you choose your AMS system, focus on systems that will achieve high precision and sensitivity, especially for these low concentration, low ratio samples, at picking the right instrument for the job. The ANSTO instrument's been phenomenal for this, but pick the right instrument for the job. And then once you have all of those conditions met, you get this amazing, unique, and important data on past and future coastal change and processes. Here's an example on the right here from one of the sites in the UK, where we reconstructed it for the last several thousand years, and then actually use that to make predictions of future change at this rock coast. Thank you very much for your attention, and I look forward to talking with you more in the breakout session.